You know, have you ever really stopped to think about the medicine you take? What actually guarantees that the pill you swallow is not just safe, but has the exact right amount of the active ingredient it's supposed to? Well, there's this unsung hero in the pharmaceutical world working constantly behind the scenes, and its name is HPLC.
All right, so here's our game plan. First, we're going to look at the big picture. Why HPLC is basically the ultimate gatekeeper for the entire pharmaceutical industry. Then, we'll shrink down and actually take a journey inside the machine itself. After that, we'll get into the really cool science that makes it all work, learn how to read the chemical fingerprints it creates, and finally, we'll zoom back out to see all the absolutely critical missions it's on every single day to keep us healthy.
Okay, so here's the fundamental problem, right? Medicines are really just complex chemical cocktails. You've got the active ingredient, the stuff that actually makes you better, but you also have binders, fillers, and sometimes potentially harmful little impurities. So the big question is, how do drug companies make absolutely sure that what's inside that pill is exactly what's on the label, down to the tiniest fraction of a gram?
And that's where HPLC steps onto the stage. You have to understand, this isn't just some other piece of lab equipment. It is utterly indispensable. It's like the ultimate quality control expert, a high-tech bouncer at the door that can take any sample, pull apart every single component, identify it, and tell you exactly how much of it is there with mind-blowing precision.
So what does this amazing gatekeeper actually look like? Come on, let's pop the hood and take a little journey through the machine to see how it takes this jumbled up liquid mixture and perfectly untangles it.
The best way to think about it is like a chemical assembly line running in reverse. First up, you've got the pump. It creates this powerful, constantly moving river of a solvent, and we call that the mobile phase. Then your sample gets injected right into that river. This whole mixture flows into the most important part of the whole setup, the column. This is where the real magic happens, the actual separation. Then, as these newly sorted chemicals come out the other side, they pass a detector, which is kind of like an electronic eye that spots each one and sends a signal. And finally, a data system grabs all those signals and draws the picture that we can actually understand.
Now, of all those parts, I really want you to focus on the column. It might just look like a simple metal tube, but it is the absolute hero of this story. It's the heart of the entire system. Honestly, every other part, the pump, the injector, the detector, they're all just the supporting cast. They exist to serve the column, because this little tube is where the real chemical sorting gets done.
So, that brings us to the science of it all. We know the what, the column separates things, but now let's get into the how. How in the world does this tube, packed with stuff, untangle a complex chemical mess?
It's a fantastic question, isn't it? I mean, it sounds like some kind of magic trick. A mixed-up liquid goes in one end, and these perfectly pure, separated components come out the other. But the secret isn't magic, it's chemistry. And it all boils down to this fundamental property every single molecule has. You could almost call it its personality. Scientists call it polarity.
Yeah, polarity. The easiest way to think about it is like tiny little molecular magnets. Some molecules are polar, think water, and some are nonpolar, think oil. And just like we all learned, oil and water don't mix. It's because polar molecules love to stick to other polar things, and nonpolar molecules, well, they stick with their own kind.
The entire process, the whole genius of it, hinges on that one simple principle: like attracts like. So what HPLC does is it cleverly turns this principle into a competition. As all those molecules from our sample get pushed through the column, they have to make a choice. Do they stick to the solid material packed inside the column, which we call the stationary phase, or do they just keep on flowing with the liquid solvent, that mobile phase we talked about?
And there are two main ways to set up this little race. In what we call normal phase, the column is polar and the solvent is nonpolar. So naturally, the most polar molecules in the sample are going to grab onto the column and hang on for longer, while the nonpolar guys get washed out first. And then you have reversed phase, which, you guessed it, is the exact opposite. The column is nonpolar and the solvent is polar. In this case, the nonpolar molecules are the ones that stick to the column, and the polar ones cruise right on through and exit first.
So which one do you think gets used more often? Well, it's not even close. Since most of the drugs and biological things we want analyzed are dissolved in water-based or polar solutions, it just makes sense to use a nonpolar column to grab onto them. And that's why reversed phase HPLC is the absolute workhorse of the modern lab. It's used in something like 75% of all methods out there.
Okay, so the components are separated, they've finished the race, they're exiting the column one by one, and that little detector is spotting them. So now what? Now we get to see how the machine turns those simple signals into a unique chemical fingerprint for our sample.
And there it is. This beautiful graph is called a chromatogram. This is the payoff. This is the final result of the whole process. Each and every one of those peaks you see represents one distinct chemical that was successfully pulled out of that original mixture. It's like a perfect visual record of everything that was inside our sample.
So how do we actually read this thing? Well, it's surprisingly simple. First, you look at the position of the peak along the bottom, the x-axis. This is its retention time. It's just how long it took that specific chemical to make it through the column. The key is, under the exact same conditions, a molecule will always have the same retention time. This is how we identify what each substance is. It's the qualitative part of the analysis.
Next, you look at the size of the peak, specifically the total area underneath its curve. It's simple. The bigger the area, the more of that substance was in the original sample. This gives us our quantitative data. It tells us precisely how much of each thing is in there. And this is the most crucial part, so I'll say it again. The position on the graph tells us what is in the medicine, and the size of the peak tells us how much. With a fingerprint like this, a sample has no secrets left.
So now that we're basically pros at how this machine works, let's zoom back out and plug this all back into the real world. Why is this ability to identify and quantify so incredibly important? Let's take a look at the critical missions HPLC is on every single day.
I mean, its job description is just massive. You wonder if that 500 milligram tablet is actually 500 milligrams? HPLC confirms it. How long can that medicine sit on a pharmacy shelf before it goes bad? HPLC runs the stability test to figure that out. Are there any tiny, potentially dangerous impurities left over from the manufacturing process? HPLC is the detective that hunts them down. From the very first steps of discovering new drugs to checking how they actually behave in the human body, this one technology is there every step of the way. It is truly everywhere.
At the end of the day, it's the invisible thread of quality that runs through the entire life of a medicine. From the second a new drug is conceived on a lab bench to the day you pick it up from the pharmacy shelf, HPLC is there, standing guard, making sure every single dose is safe, pure, and effective.
We rely on this technology so completely. But you have to wonder, as our medicines get more and more complex, we're talking about biologics, personalized gene therapies, the challenges for our unseen guardian are only going to get tougher. So the big question for the future is, what's next? How will this incredible technology have to evolve to keep protecting us down the road?